Okay, good morning, people. Today we're going to study informal logic. This is section 3.1 of the textbook. And what that is basically is, well, we've been using logic a lot in all the things we've been studying so far. We've been talking about if-then statements. We've been talking about when you say X is in A and X is in B, so that's a connective statement. But we didn't actually talk about what those statements mean or what they mean mathematically. So what I want to go over today is how to look at a sentence and see is it a mathematical statement or not, because sometimes we write ambiguous things or imprecise things. The second thing I want to go on is when you have a statement, how do you know if it's true or false? Can you identify that? Sometimes you can't identify. Okay, so let's get started. What exactly is a mathematical statement? Actually, instead of that, I prepared a poll question for you on mathematical statements. So instead of just telling you directly what a mathematical statement is, here's a question for you. I want to know, well, if you read the textbook, you might be familiar. But if you didn't read, I just want to see what you think is a mathematical statement. So here's 8 different statements, and I'll put up the poll. Which of these statements that are on the screen here, 8 of them, which of these are mathematical statements? Okay, I'll give you 3 to 4 minutes to solve it. Okay, so think about, I'm not going to tell you what a mathematical statement is quite yet. I'll tell you in a couple minutes. But I'm curious to see what you think a mathematical statement is. I'll use that to figure out what to say. And yeah, this is multiple choice, meaning you can pick any number of the statements there. Some of these are mathematical statements, some of them are not. Think about what features a mathematical statement should have. And then think of which of these statements have those features. Let me give you a hint. A mathematical statement must be either true or false. If it's not true or false, if you can't look at it and evaluate its truth value, then you can't tell if then it's not a mathematical statement, okay? So this is just a little hint for you. Okay, awesome. So let me end the poll here, and I'll show you the results. I like these. I think, I would have liked it no matter what, I guess. But all right, let's take it up. So yes, let's talk about these first two, A and B. So, wow, 67% of the class thinks A is a mathematical statement. Well, I have to be able to look at this thing and quantify its truth value, right? And it looks like it's true, right? For all real numbers, X and Y, it would be true, but I didn't say X and Y were real numbers. I didn't say anything about X and Y. I didn't tell you what X and Y were. X could have been an elephant and Y could have been a house. And so it's elephant plus house, absolute value. This doesn't make any sense, right? This is not a mathematical statement. It looks like one because it looks like a theorem we've seen before, the triangle inequality. That doesn't make it a statement. A statement has to be quantified. So this is not a mathematical statement. So this one's not. This is not a mathematical statement. And the reason is because it's not quantified. And what that means is, had I said, how can I have corrected this? How can I correct this to become a mathematical statement? What sentence can I add before it? Yeah, exactly. Let X and Y be real numbers for all X and Y real numbers. Yep. So a correction could be, I feel like I shouldn't be using red and green, but yeah, correction would be for all X, Y real numbers, real numbers, blah, blah, blah. That would be a way to turn it into a mathematical statement. Okay, so because this isn't quantified, we call it a predicate. A predicate is something that's not a statement, but if I quantified the variables in the statement, it would be, sorry, if I quantified the variables, it would become a statement. So this is an example of a predicate. Okay, how about B? B is false. B looks false because it's a statement we're not familiar with. Or sorry, it looks like a triangle inequality, but backwards. But it actually is not even a statement, again, because it's a predicate. So not a statement. It's a predicate. Okay. Okay, let's try the others, C and D. So let's see what people said. People said C is 62%. Fewer people said that this one was a statement than said A. And actually, this one is a statement. And you might look at it and say, oh, well, it's saying that if T is a real number, then T is positive. But what about like T equals negative 100? That's not positive. But it doesn't matter if it's positive or not. Well, sorry, it doesn't matter if the statement's even true. It just has to be a quantified statement with a true or false value. And this one's false. This is a statement. It's just false. There's nothing wrong with a false statement. We write false statements all the time. You guys write false statements on Piazza all the time, but they still count as statements. They're just false. So, I'm just kidding around. Okay. I could say something like Hassan is a millionaire. And it's not a true statement, but it's still a statement because it has a false value. The same for the second one. If T is a natural number, then T is positive. This one happens to be true, but that doesn't mean it's that doesn't change whether or not it's a statement. It just happens to be true. Okay, so a lot of people said D was a statement. Good, indeed it is. But I hope we learned that a statement doesn't have to be true in order to be a statement. Okay, let's see. E, every integer greater than 2 is a sum of 2 primes. Interesting. Every even integer. So 4 is 2 plus 2. 6 is, let's see. Which one is 6? 6 is an even integer. And is it a sum of 2 primes? I guess it's 5 plus 6 is a sum of 2 primes. But it doesn't, okay. Wait a second. I'm going to pause for a second. Yeah, I forgot about, you can add the same number twice. Yeah, 6 is 3 and 3. 8 would be, what, 5 and 3, right? 10 would be 7 and 3, for example, right? But the statement's saying that every even integer. Okay, this problem, someone said in the chat, is Goldbach's conjecture. So this is actually an open problem. If you solve this, you're gonna get famous. But is it a mathematical statement or not? Because a mathematical statement has to be true or false. And if it's an open problem, that means nobody knows if it's true or false. That doesn't mean it's not true or false. It just means it's not known. Us it is a statement. It either is true or it's false. And it doesn't matter if I don't know or if you don't know or if any of us know. It could be that there's some weird alien out there that does know, or somebody 1,000 years ago knew and never wrote down the proof. So it is a statement. This is a statement. It's just unknown. This is a statement, but its truth value is unknown. It still has a truth value. We just don't know it. Okay. Am I good? Okay. And F, let Z be a real number. Only 20% people said this one. And this one's not a statement because it doesn't have a truth value. Let Z be a real number. Okay, is that true or false? It's not a statement. Okay, G, very few people chose G, good. G is just a number. Pi plus root 2 squared plus 3 is just a number. That can't be true or false. So it's not a statement. If you want, you could say that this is an expression, but until I state something that I can verify about that expression, it's not a statement. Okay, and the last one, only 58% of people said that this one was a statement. It actually is a statement because it's just a number, it's just a number, but it asserts that this number equals 4. And that's an assertion, that's a statement. It can be true or false. In this case, it's false, but it's still a statement. This is a statement. This is a false statement. Okay, so to summarize, statements have to be true or false. Or let me say it like this, must have a truth value, true or false. And it doesn't matter if you don't know the truth value. If it has a truth value out there somewhere, even if you don't know it, some alien could know it, that still counts as a statement. It would just be a conjecture. Like this one, actually, I should have written that down. This is called Goldbach's conjecture. You should look it up. A cool problem from number theory. Okay. Another thing is statements must be quantified. Or let me write it like this. Yeah, statements must be quantified. And then I'll say that an unquantified statement is known as a predicate. So if a statement has unquantified variables, then it's not a statement actually, it's a predicate. I think this is basically everything we learned from this example. Everyone got it? Now listen, if you're in a lot of you in computer science, if you type if 8, then some run some code. If 8, then do this. That's going to run the code because I don't know if all computer programs do this, but I think in Python, if you type if 8, it'll just take 8 as it's a number. It's not a statement, but it'll still interpret that as true. So that's a quirk of programming. That's not the mathematical perspective. So sometimes the programming overlaps with what we do in MAT102, but sometimes it doesn't. Okay, so just be careful a little bit. Okay. Okay, next thing about statements is how can I think some of these were if-then statements. And I'll talk about that maybe on Wednesday, a little bit today. But today I want to talk about how to quantify a statement. What kind of quantifiers are there? And and the connectives, the way it's combining statements. So if I have two statements, P and Q, so let me say let P and Q be two statements, then I can combine them and I can still make a new statement. So P and Q would be true if, and this is going to sound stupid, if P is true and Q is true. So if both P and Q are true. Just literally the definition of the word and. If both P and Q are true. If one of them is false, then the entire compound statement is false. So false otherwise. Okay. P or Q, in computer science, or might mean something else, I don't know. But here it means that only one has to be true, at least one. At least one of PQ is true. Both could be true. That counts as true, or false otherwise. So as an example, let's say if X is a real number, then I don't know, X is, oh, sorry, that's not a or statement. Let's say 2 is greater than 0, or 2 is irrational. Okay. Is 2 greater than 0? Yes. Is 2 irrational? No. But one of them is true, and it's an or statement, so the entire or statement evaluates to true. I'm pretty sure if you did plug this into a Python, then it would you would get true. Okay, for example. Okay, quantifiers. This is what I was talking about earlier. How do you turn a predicate into a quantified statement? So you can say, one way to do it is to say for all x in some set, then you have some statement involving x. So let's call it P of x. So here P of x is some statement involving x. sorry, some predicate. I shouldn't say some statement, some predicate involving x. So this is, some people call this a universal quantifier because I said for all x in my universe, A is some set. So an example would be for all integers z, or x and z, x is even or x is odd. Okay, this is definitely a true statement. Okay, so this is called the universal quantifier. There's also another one called an existential quantifier. This is that says there exists x in A such that P of x. Okay, maybe I should highlight these. This is called the existential quantifier. And all this means is that it must be true for at least one, let me say P of x must be true for at least one x in A. Okay, and then as an example, let's say there exists an integer z such that x is greater than or equal 5. This is a true statement. I think I should have written true here as well. Okay. Okay, so these are all mathematical statements because this has a truth value. Okay, so let me give you another poll question about this. Unless there are any questions. Are there any questions about how quantified statements and connectors work? All conjectures of statements. Yeah, all conjectures of statements. Yeah. Okay, here's the next poll question. Here's 5 statements. Can you tell me which of these are true? And oops, sorry, one sec, I have to launch a poll. Can you tell me which of these statements are true amongst these 5 statements? And these are all quantified statements, but they're also complicated because they say for all and they have there exists, and I've permuted them in various orders. And I've also used and or, I've combined the connector statement, the connectives with the quantifiers. Okay, I'll give you maybe 4 minutes for this. Okay, so let me take up the poll now. So which of the following statements are true? Let me share the results. So a lot of people think A is true. Let's check. I actually don't know which are true and which are false. Let's try. So for all x in bigger than or equal 1, there exists a real number y such that x is less than or equal y and x squared is greater than or equal y. Okay, that's not bad. Because if x is greater than or equal 1, okay, yeah, let me just say this is true. And the reason is, here's a proof sketch, that if x is greater than or equal 1, then if I draw a number line, x would be here, and then x squared would be bigger. X squared is always bigger than or equal to x. So maybe I can say that. X is less than or equal to x squared. So if I draw a number line, say x is here and x squared is here, then I can pick any number in between. I can pick any number in between, and that's my y. And then x would be less than or equal y, and y would be less than or equal x squared. So this is a true statement. Just visually, you can see it. You can think about how to rigorously prove it. Okay. There exists x greater than or equal 1 such that for all y real numbers, x is less than or equal y, and x squared is less than less than or equal, sorry, greater than or equal y. Okay, yeah, this looks false. And the reason it's false is I want x less, here, let's say a proof that it's false, proof of falsity is, well, here, actually, that's not a good way to put it. Let's just say counterexample. Counterexample. So, oh, sorry, what am I trying to say? Not a counterexample. I'm trying to say that it's false, right? So proof of falsity was correct. I don't know why I erased that. Proof of falsity. Sorry if your notes are getting all messed up. Proof of falsity. Suppose that such x exists. Then x less than or equal y, and x squared is greater than or equal y for all y. For all y. That means if I take y equals 1, I need more space now. I can take any y I want, apparently, according to the statement. So then x is less than or equal y, and x squared is greater than or equal y. So x is less than or equal 1, and x squared is greater than or equal 1. But if x is less than or equal 1, this directly implies that x equals 1, because we already know that x is greater than or equal 1, and now I'm saying it's less than or equal 1, so it has to be equal 1. Okay? But now take y equals 2, say, then x squared is not greater than, let's say 1 squared, yeah, x squared is not greater than or equal 2. So I've got a contradiction. Okay, I'm supposed to find one value of x that satisfies this inequality for all y, right? So that means that I have to say there's one value of x such that every real number is between x and x squared. Maybe I should have just said that. Every real number. But the second I pick some real number over here, it's false, right? So if you don't like this proof, just look at this picture here. This picture has all the information in it. Okay. How could it be that there's one real number x with this property, that there's always a number between x and x squared? Or sorry, every real number is between x and x squared. It doesn't make any sense. Yeah, here, I'll do an explanation like that for the next question. So for C, people are saying it is, so B people thought was true. It's definitely not true. For B, for every real number x, there exists a y such that x is, this is different. X is strictly less than y. Or x squared, maybe I won't take up all the parts, but x is strictly less than y, or x squared is greater than or equal y. Let's see. So is this true or false? People are saying it's, 50% of the votes say it's true. Let's see. So let's try to draw a picture again. Again, since x is bigger than 1, I can say x is between x here. Is this one true? For all x, there exists a y. I think this one is true. This one is true, okay? Because if x is strictly, I think this is true. If x is strictly bigger than 1, then there's some gap between x and x squared. Sorry, yeah, between x and x squared. And I can just insert any y in here. If x is equal to 1, which is a possibility, then x and x squared are the same. They're both 1. But now I can just take y to be 1 as well. And then y is the value I need. And I only need to say that there exists y. So I only need one value of y. I'll just take y to be 1, and that does it. So in either case, in the first case, I could just take y to be any midpoint. I could even take y to just be x squared. well, let's just say x plus x squared over 2, the midpoint. Okay, so this statement's true. Okay, so some people are saying if y equals 1 doesn't work. I think it does work, right? Because I only need one of these statements to hold. So if x equals 1, let's say x equals 1, right? Then does there exist some y with this property? Sure. Let's take y to be 1. I could even take y to be 2 if you want. Here, let's just pick y to be 500. If I pick y to be 500, then certainly x is less than y. So the statement's true for x equals 1. And if x is bigger than 1, I can just, that means that there's some gap between x and x squared, so I can just insert y in the middle. So either way, there's always going to be some y bigger than x. Who cares about the second statement? It's an or statement. So at least as long as this first one's true, the whole thing is true. Okay? Okay, and in the interest of time, maybe I won't take up the last couple, but maybe I can at least tell you if they're true or false. There exists x such that for every real number, either y is strictly bigger than x, or x squared strictly is greater than or equal y. I should have written down the answers to these. There exists x such that for all real numbers y, x is less than y, or x squared. So if x, yeah, I don't think that's true. This seems false to me. Usually when you quantify over all, some real number x with some property that holds for every real number, usually you've got a problem, right? So if x is 1, let's see. Let me just do some rough calculations here. I really should have written down whether or not these statements are true or false. So if x exists in 1 to infinity, then let's see. I can take y to be 1. So let's see. So x is less than 1, or x squared is greater than or equal 1. And none of these are surprising. Maybe if I take y equals 2, I can see that x is less than 2, or x squared is greater than or equal 2. Okay, looks like I should have written down the answer for these. I just randomly permuted these symbols. Sani, do you know if this one's false or true or false? Let me see here. The statement's too many. Here, I'm gonna pause the recording while I figure this out. Okay, I think I figured it out. It's true. Thank you. Sani said now yes as well. It's true. I just need to show that there exists some real number, x. And so let's say x equals 1. This number has the property because x equals 1 works because every real number y is either greater than 1 or less than or equal 1. It makes perfect sense, right? Because x squared and x are both 1. Yes, I think that's how I came up with the problem, and then I just forgot. I should have taken some notes. Does it make sense why, sorry that I blundered there, but does it make sense why this one's true? Okay, good. I see. So for this last one, okay, you know what? I have 10 minutes left and I had an exercise for you guys. So instead of blundering myself over this last one, let me show you that exercise, okay? D is true, okay? D is true. So here's the last exercise I want to give you. This should be, I hope it's fun, but I want to give you maybe more time on this than we have. We only have 10 minutes. So here's a bunch of sentences. For all there exists such that, well, these aren't sentences, maybe phrases. Just some random, none of these are statements because they're not quantified true or false statements, but still try to combine these and make a statement of your own, an actual legitimate statement. Try to make one that's false and try to make one that's true using only these things. And you can use each one more than once. So here's an example. Let A be a subset of R, of the real numbers. Then there exists a subset B of A such that Y is an A for every Y in B. Okay? So for example, that's a statement because it's either true or false. And it's well quantified as well. I said let A be a subset of the real numbers that quantifies A. And here's another one, let A be a subset of the real numbers. And for every X is an element of A, there's a set B of real numbers such that B is a subset of A. And if Y is in B, then Y is greater than X. So it's just this big mess of stuff, but ultimately it's either true or false. So this is a statement as well. So maybe don't make them as complicated as this, or you might have a hard time verifying if it's true or false, but try to make a true statement out of this and try to make a false statement out of this, okay? I'll give you 5 minutes and then I'll take it up. Okay, so by the way, this E now I'm pretty sure it's true. There exists X with this property. Let's take X equals, it doesn't matter almost. Let's take X to be 2, right? Then for all Y in R, I need to verify the statement that either 2 is less than Y or 4 is greater than Y. And this is definitely true, right? If I draw a number line, then and 2 is here and 4 is here, then I'm saying every real number is either greater than 2 or less than 4. And that's absolutely true. 4, for example, is greater than 2. And 2, for example, is less than 4. Any real number has one of these two properties. So this is actually true with X equals 2. Okay? Okay. Sorry it took me a while to figure that out. I should have prepared it better, but I hope that makes sense. Okay, so let's take up this activity. What did, here, I'll make 2 categories. Oh, sorry, this was something else. I'll make 2 categories, false statements and true statements. Can someone give me an example of Can someone give me an example of a true statement that uses these phrases? What did you guys come up with? If A is a subset of B, yeah, yeah. If A is a subset of B, yeah, okay. I think you have to quantify A though. Okay, so Burgess says if A is a subset of B, then for all X in A, it's gonna, okay, I'm gonna have a hard time writing these up properly. For all X's in A, X is also in B. So you can write we have if you want. Sometimes you have to put something like that in the middle. For all X in A, we have X in B. I think you need to quantify this statement. Because if you just say if A is less than B, you didn't say what A and B were yet. So you should say for all A subset B, or sorry, A subset of the real numbers, and B a subset of the real numbers. So now it's quantified. So now I think it's a valid statement and it's a true statement. It's just saying whenever I have 2 sets, if one is a subset of the other, then, I mean, this is the definition of subset. So this is true, okay? For all X belongs A, there exists Y belongs B, such that A is a subset of B where X is greater than Y. Okay, yeah? I think what you have to do is quantify these sets. If you just say for all, if you just say something, if you don't say what A is in advance, then it's not clear. Like A could be, if I didn't write this down, A could have been an elephant. And it doesn't make sense necessarily to say that an elephant is a subset of, I don't know, if B is a tree, right? So you have to say specifically what A and B are before you make a quantified statement. Can someone give me another true one? Let A be a subset of R. For all X, there exists a Y and B, such that A is a subset of B or B is a subset of A. Okay. So I don't think that one's quite good because you said something about, I guess that is technically a statement, but you didn't say anything about what X is. And you didn't say anything about what Y is. Can someone give me a true statement that involves these inequalities here? Here, I'll give you one. So for all A as a subset of B, or sorry, a subset of real numbers, and X in A, there exists a set B, a subset of A, such that Y is in, such that X is in B, let's say. Maybe yeah, X is in B. So I think this is a true statement because I could just take B equals A, which is a stupid true statement, but I'm just saying that there exists some set that X belongs to. Well, I might as well just take X to be A because I already said that X belonged to A. This is a stupid example of a true statement. Okay, how about false ones? Excellent, good. So Michael Fillar, is that an example of a true statement or a false statement, the one you just wrote down? True, interesting. Okay, let's write that one down. So for all, oh, I'm out of time here. For all A, a subset of R, and B, a subset of R, there exists X in A, Y in B, such that X is greater than Y. So this one, is it true? For every set A and every set B. What about if I take A to be the set consisting of just one and B consisting of B as the set of 0, let's say? No, let's take B to be the set consisting of 2, right? Then you can see that there's no element of B that's smaller than an element of A. I'm trying to say that Y is less than X. So this one's actually false. Move it there. Okay, one more. Let A be a subset of R. Let A be a subset of R. Then for all X an element of A, if B is a subset of A, okay, yeah. Let, I guess, did I say let? Oh yeah, I did. Let's valid. I mean, I used let as well. Good. I'm gonna finish off here. Let A be a subset of the reals. Then for all X and A, if B is a subset of A, then X is in B. That's definitely not true. That's definitely false. Because I could take A to be, who knows, the set consisting of just one, and B to be the empty set, and X to be, well, 1, because then X is an A, B is a subset of A, and that B looks really weird. B is a subset of A, and yet 1 is not in B because B is empty. So you're right, this one is false. This is an example of a false statement. Okay. Okay, so I think I went like 3 minutes over time. Sorry about that. Are there any further questions about how any of this works?